Hello viewers, today we are going to discuss the topic reversible and irreversible processes. This is a very important topic of thermodynamics. So let us start with reversible processes. Reversible process. The definition of reversible processes: if a process is carried out in such a way, if a process is carried out in such a way that at the end of the process, system and surroundings are restored to the initial state without leaving any traces on the universe is called a reversible process. So the definition says that if a process is carried out in such a way that at the end of the process, the system as well as the surroundings are restored in the initial state without leaving any traces on the universe, is called a reversible process. Now, what is the meaning of this definition? That if we have a PV plane and there is a system which exists in state 1, and this state 1 is defined by P1, V1, pressure is P1, volume is V1, and the system goes from state 1 to state 2. This is state 2, and this state is defined by P2 and V2, and this process is carried out in such a way that all the intermediate states are equilibrium states. So the system moves from state 1 to state 2 through all the equilibrium states. This process will be a reversible process if at the end of this process the system and surroundings are restored in the initial state. What is the meaning of this? That if a system proceeds from state 1 to state 2 through the equilibrium states, and if the system can come back from state 2 to state 1, and at the end of this process there is no net effect on the system and surroundings, then this process will be reversible process. So what is the meaning of this net effect? Zero net effect on the system and surroundings. That if when the system was moving in this direction from 1 to 2, suppose the name of this path is A, so the system proceeded through 1A2, the path is 1A2, and suppose there is a work transfer 1W2 while system is moving from state 1 to state 2, there is a work transfer, or we can say there is a work output. Then when the system goes from state 2 to state 1, that is 2W1, then this 2W1 should be equal to 1W2, and it should be in the reverse direction. So there is no net work transfer through the system. Now if there is a heat transfer, similarly if we say that there is a heat transfer when the system proceeds from state 1 to state 2, that is 1Q2, so the heat transfer when the system proceeds from 2 to 1, that is 2Q1, this 1Q2 should be equal to 2Q1, and it should be in the reverse direction. If initially it was heat supplied to the system, then in the reverse process it should be heat rejected from the system. So net heat transfer should be 0. So we are seeing that net work transfer is 0 or net heat transfer is 0. It means that all the energy interactions should be in the reverse direction and the total energy interaction should be 0. So this is the meaning of a reversible process. Now if we take an example of a practical life, suppose I am at a particular location. This location is suppose location A, and this particular location is suppose B, and I want to move from state 1, so this location 1 to location 2, and let us take that this distance is 30 kilometers, and I am using my car for moving from state 1 to state 2, and the mileage of my car is suppose 15 kilometer per liter. 15 kilometer per liter. So if the standard conditions exist, then at least I should have 2 liters of petrol to move 30 kilometer distance. Okay, so we are considering that there are standard conditions, and I have 2 liters of petrol in the petrol tank of my car, and I move from state 1 to state A to state B. So when I reached my destination, that is state B, theoretically we can say that the petrol tank of my car will be completely empty, right? Now if I come back from B to A, if I come back in this direction from B to A, then this petrol which was consumed in the motion from A to B should be regained in the petrol tank. The same amount of petrol, that was 2 liters, this 2 liter of petrol should come back to the petrol tank. Not only this, the exhaust which was released in the environment by the car should also come back to the engine, to the vehicle. If there must be some wear and tear in the car also, that should also be restored to the initial state. If all these conditions are satisfied, then we can say that this process is reversible. A to B, this is a reversible process. So now with this example, you can understand easily that such processes are not possible. Okay, this reversible processes are not possible. So the practical processes are irreversible processes. Okay, the practical processes are irreversible processes. So reversible is a limiting condition, that if a process is reversible, then at the end of the process all the conditions will be restored in the initial state, right? So this is the meaning of reversible process. So reversible processes are theoretical processes and irreversible processes are practical processes. Now we have to see what is the reason that the processes are not reversible and they are irreversible practically. And one more thing I would like to mention here, that as we have taken the example that initially the system is in state 1 and finally it is state 2, and if the process is reversible, then all the intermediate states will be equilibrium states. So if I join all the equilibrium states, then it gives me a path that is 1, 2, or we can write 1A2. The path is 1A2. This is a reversible process. So the condition for being a reversible process is that all the intermediate states should be equilibrium states. Okay, so if the process is irreversible process, this was PV. Again we are drawing a PV diagram, and if the process is irreversible process, then the intermediate states will not be equilibrium states. So we cannot draw a firm curve or a firm line between these two states. This will be a dotted curve. This will be a dotted curve. So this is an irreversible process. Irreversible process. And this is a reversible process. This is a reversible process. So reversible processes are drawn with firm curve or firm line on a thermodynamic plane, and irreversible processes are drawn with dotted lines between the two states on a thermodynamic plane. Okay, so this is an important thing. Now, we'll discuss the causes of irreversibility. Causes of irreversibility. So there are two causes of irreversibility. First is lack of equilibrium. Lack of equilibrium. And second is due to dissipative effects. This is lack of equilibrium during the process. Okay, this is lack of equilibrium during the process. And in lack of equilibrium we have lack of pressure equilibrium or mechanical equilibrium. Second is lack of thermal equilibrium. And third is free expansion. And in dissipative effects we have due to friction, and second is pedal wheel work transfer. So let us discuss them one by one. See, we are discussing the causes of irreversibility. We are saying that theoretically the process should be a reversible process, but practically the processes are irreversible process. So we must understand what is the reason of this irreversibility. Okay, so the first reason we have mentioned here is lack of equilibrium. We know that what is the meaning of thermodynamic equilibrium? Thermodynamic equilibrium is when the condition of mechanical equilibrium, thermal equilibrium and chemical equilibrium are satisfied at the same time, right? If these three equilibrium conditions are satisfied at the same time, then we say that the system is in thermodynamic equilibrium. Now, lack of equilibrium is that out of these three, one or maybe more will not be satisfied. So first we are taking lack of pressure equilibrium. See, if we have a system like a piston cylinder assembly, and we have a gas here. So this gas has a pressure, volume, temperature, and we are considering that the pressure of this gas is higher than the atmospheric pressure. This piston is in this position. This is suppose position 1. It is in this position, and on the left side of the piston there is a pressure of the gas, and on right side we have atmospheric pressure. So if this pressure of the gas, if this P gas is higher than the P atmospheric, then this piston will be pushed. This will be pushed by the gas, and this piston will move in this direction. And we can understand that if this difference is higher, then the speed of the piston will be higher, right? So if this process has to be reversible, then this pressure difference should be very, very less. Or we should understand in this way that this piston is moving because of the pressure difference. The more is the pressure difference, the more will be the speed of the piston. And if this piston is displaced to a new position, that is this is the new position, state 2, then this piston has been displaced, and this process is not a reversible process. It is an irreversible process, because we cannot bring back this piston in this position without any external effort. right? So this process is an irreversible process, right? This is a practical process and this is an irreversible process. Now we must see what is the reason that this process is irreversible. The reason is the pressure gradient, the change in the difference in pressure. The more is the pressure difference, the more will be the irreversibility. Okay, and if we want to make this process a reversible process, then what should we do? We should reduce this difference. We should reduce this difference of pressure, or we can say pressure gradient. If this pressure difference is very, very less, then all the intermediate states will be equilibrium states. If this pressure difference is very, very less, it is infinitesimally small, then this piston will be displaced little bit in this direction and then it will stop. Again it will move and it will stop. So in this way we can say that all the intermediate states are equilibrium states and the process is a reversible process, right? So we can see that if this pressure gradient, the pressure gradient is higher, then irreversibility will be higher. If we make this pressure difference very, very small, infinitesimally small, then this piston will move in a very, very slow speed. And this practically, this is not desirable. Okay, if this piston moves very slow, then the work transfer will take a lot of time, okay, to occur. So this piston, practically this piston should move fast so that we get the work output in small span of time. So if this piston pressure difference is very small, then it will take infinite time to reach from this position to this position, and this is not desirable practically. Okay, so that is why practically the processes are irreversible, right? And we cannot avoid this irreversibility because we cannot avoid the pressure difference, right? So this is the reason of irreversibility, because of lack of pressure equilibrium. Similarly, the second is thermal equilibrium, lack of thermal equilibrium. Suppose we have a container in which we have a gas and the temperature of the gas is T gas and the environment temperature is T atmospheric, and we are considering that the gas temperature is higher than the atmospheric temperature. If the gas temperature is higher than the atmospheric temperature, then what will happen? There will be heat transfer. There will be heat transfer from gas to the environment. And we know that the heat transfer rate is directly proportional to the temperature difference. If this temperature difference is more, then the heat transfer rate will be more, right? And practically, if you want to reject the heat, or if we want that this heat transfer should take place, then this temperature difference should be more. And this will be an irreversible process because we cannot reverse this process. The heat cannot be transferred from environment to the gas without any external effort. So practically this process is an irreversible process. Now, what can we do to make this process a reversible process? We can reduce this temperature difference, that is the temperature gradient. So if we reduce the temperature gradient or this temperature difference, this heat transfer rate will be very, very slow. And it may take infinite time to transfer this heat to the environment. But we know that in a heat transfer, practically in a heat transfer process, there is a finite temperature difference between the two bodies. So if this finite temperature difference exists, then only there will be significant, or we can say the heat transfer will be in the required rate. Okay, so this is the reason of irreversibility, right? This is the reason of irreversibility, that due to lack of thermal equilibrium. Thermal equilibrium is that the temperature difference exists within the system or between the system and surroundings. So there is a temperature difference. Because of that only there is a heat transfer. And if we want that this heat transfer should have a significant rate, then this temperature difference should be a finite temperature difference, right? So this is the meaning of lack of thermal equilibrium, and this is the meaning of irreversibility due to lack of thermal equilibrium. Now we are taking the case of free expansion. So free expansion is that if we have a compartment if we have a compartment, and this is divided in two parts. This is A and this part is B, and the walls are made of some insulating material. This material is insulating material, that is, we can say insulation. And the gas over here, there is a gas over here. It has pressure P, volume V, temperature T, right? It has certain properties. And in this particular portion, we have vacuum. We have vacuum in portion, in part B. And this is a diaphragm. This is a diaphragm. So, and there is an insulation. It means there cannot be any heat transfer from this gas to the environment. Now, if we remove this diaphragm from here, then this gas will rush towards part B. And the moment we remove this diaphragm, this gas will occupy the whole volume. Now the volume will be this much. This gas will occupy the whole volume. And this process is not a reversible process, because we cannot reverse the process. We cannot, once the gas has occupied the whole volume, it is not possible without any external effort to bring back this gas in this compartment A and to create a vacuum here. So this is an irreversible process. And this particular expansion is called free expansion or unrestrained expansion. Reason is that when this gas expands in this particular volume, there is no pressure over here to oppose this expansion, right? So there is no restriction. That is why this is called free expansion or unrestrained expansion. So this is also one of the reasons of irreversibility, right? So we can try to make this process reversible. What will we do? We'll make number of layers of this diaphragm here. If we remove one, then this gas will expand a little bit. Then we will move the another layer. Then this will move further in this direction, and ultimately passing through all the equilibrium states, this gas will occupy the whole volume. So in this way, we can move from irreversibility towards reversibility, right? So to the bottom line is that if we want that the process should be reversible, then we must see the gradient. What is the gradient because of which this process is taking place? If this gradient is very, very small, it is infinitesimally small, only then the process will become a reversible process, or it will move. The gap between the reversibility and irreversibility will be very, very narrow if this pressure difference is very, very small. Gradient, if the gradient is very, very small. Okay, so I hope you have understood the meaning of lack of equilibrium. So this is lack of equilibrium, we have already discussed. Now we go to the next cause, that is due to dissipative effects. So first is due to friction. First of all, we are discussing due to friction. Now, how does this friction cause irreversibility? Now, suppose we have a moving vehicle. Suppose there is a cycle. We are moving on a cycle and the wheel is moving with a particular velocity. Then we can calculate the kinetic energy of the wheel. This wheel is moving and I want to stop the cycle. Then what will I do? I will apply the brakes. So what is the process of applying a brake? That I will press the brake, and the brake shoe will come in the contact of the wheel or rim of the tire, and this will retard the velocity, this will retard the motion of the cycle, and ultimately this wheel will come at stop. Now there was a kinetic energy in the wheel when it was moving. Now it has stopped. So where has this kinetic energy gone? Because energy is conserved by the energy conservation principle. So this energy has been stored in the material of the brake shoe in the form of molecular energy, or we can say internal energy, right? So, and we can check it also that if you touch the material of the brake shoe, it becomes hot. The temperature, there is a rise in temperature of the material of the brake shoe. Now, is this process reversible? Can we do this, that we supply the energy stored in the material of the brake shoe to the rim in the reverse direction and this wheel will start moving? No, it is not possible. So friction is also one of the cause of irreversibility. This vehicle has stopped because of the friction between the brake shoe and the wheel, right? So friction is also a cause of irreversibility, and this friction cannot be avoided. So there is an irreversibility in the process. Now, second is pedal wheel work transfer. If, let me erase this. Now, if we have a container, and there is an insulation, this body is insulated, and there is a fan over here which is connected with a pulley, and there is a weight over here. Now, if we move this block over here, this block will run this fan, and if there is a gas, or we can say air, there is a gas or air here, then this stirrer, this is a stirrer, this stirrer will work on the gas, and after some time we can check that there is rising temperature of the gas, okay, because this work is being transferred to the gas, okay, there is work done on the system. Our system is this gas, so there is a work transfer in the system because of this stirrer, because of the motion of the stirrer, and since there is an insulation over here, so heat cannot be rejected to the environment. Now this work transfer is stored, when it is transferred to the gas, it is stored in the gas in the form of molecular internal energy, and this process will be irreversible. Why? Because this stored energy cannot be supplied back to the fan, and this is not possible that because of this energy this fan will start moving. So this is an irreversible process, right? And this fan is giving work, or it is transferring work to the gas, but it is not possible that this energy which is stored in the gas is supplied back to the fan, and fan will start moving. So that this is also an example of irreversible process, right? So these are the reasons of irreversibility. There may be other reasons also, but we have discussed the important reasons, okay? So I hope now the concept of reversible and irreversible process is clear. So we are keeping this much only for this particular class. In the next class we'll discuss about the work transfer and heat transfer.